This video is focused in on work energy for particle kinetics. You've already covered it in a lecture, and at this point you've gone through two forms of it. One where you calculate it as kinetic energy plus work from position 1 to position 2 is equal to the final kinetic energy. You've also seen another form of it where you've had kinetic energy at state 1 or position 1, potential energy at position 1 associated with conservative forces, gravity and spring, plus work done from 1 to 2 is equal to T2 plus V2. And my preference is always for that sort of form of it. But in terms of learning objectives today, the focus is on work energy, discussion about conservative forces, and finally going into conservation of energy. And really the idea is to sort of focus in on when you use these problems. And when you use these problems is always going to be the same, which is you have force, velocity, and distance. So that's really important to keep in mind as you're studying, doing the homework, and ultimately as you're looking at old exams and you're sitting in on the midterm and final exams. So let's start with something a bit straightforward. An automobile of 1,800 kilograms is driven down a 6-degree incline at a speed of 100 kilometers an hour when the brakes are applied, causing a constant total braking force of 6,500 newtons. Find the distance traveled by the auto as it comes to a stop. So really, in terms of the motion, that's all that's happening. It's moving down the ramp. And you know that it's a work energy problem because one, you have, and this is where we cheat a little bit, you have weight here. You've got mass really, but we're going to solve it as a weight problem. You've got speed here, and you're asked for a distance, and you have another force here. So you have force, velocity, distance that's going to appear immediately in this problem, and you know how to solve for it. So force, velocity, distance. And really you're going to look at the change in kinetic energy. What's the work required? And I'll do it two separate ways. It's not really that different. How much work is required and what are the influences of conservative forces. So if we do that, we can sort of say, well, this is position 1 and this is position 2, and the car is moving down the ramp and it's traveled a distance x. And of course, at this point, you've done this so much, but we need to convert the 100 kilometers an hour into meters per second. So if you do that, you end up with a velocity of the car, which is 27.8 meters per second at position 1. And at position 2, you have 0 meters per second. So if we do that, we can say, well, T1 kinetic energy at position 1 is 1/2 mv1 squared, 1/2 1,800 kilograms, 27.8 meters per second squared, or 694.4 kilojoules. At position 2, that's 0 meters per second, and that's 0 joules. So good, no problem. So now if I look at it a little bit more, I've got the braking force, which is opposing motion, I have normal force, and I have the weight. And the weight is not in the direction of motion. Braking force is, normal force is. So I just need the component that is acting in the direction of motion. And that's going to act down the ramp. And so I should have drawn this into the figure. I have x and y defined this way. X is down the ramp and is positive. So if that's the case, work 1 to 2, there is negative braking force because it's in the negative sense. And I have a component of weight which is acting in the direction of motion, mg sine theta x. And we know that everything else from the weight doesn't play a role because it's not traveling in the same direction as motion. So we end up with a term that goes as minus 4.65 kilonewtons times x. So now if I put in the expression, I've got kinetic energy at position 1, work from 1 to 2 is equal to final kinetic energy of the system. And I can solve through because x is the only unknown here. I've got x here, x here, x here. I already know what this is. I can solve for T1, and I get 4.7, or T1 over 4.7 kilonewtons, or a distance of 149.2 meters. Super. If I had done this using conservative forces, there'd be a little difference. Then I look at what the path is. I don't look at the component of force. At least that's how I think about it. And so I'd say, well, T1 plus V1 plus work 1 to 2 is equal to T2 plus V2. In that case, I have V1, which is going to be the component of potential energy, gravitational potential energy at position 1, mgx sine theta. That's how high it is. And I have work done by the braking force, which is a non-conservative force. That is, if I went back up the ramp, I would have double the braking force, essentially, as it opposed motion in both sense. And what I've done is, sort of without telling you, is set my datum as 0 at the bottom of the motion. So those two terms go away. So that ends up being the exact same relationship and the exact same result. So here's another one. So here's a problem I always like, absolute dependent motion. And I have a block which is 25 kilograms, and a block A, and a block B which is 3 kilograms. So block A is over here, block B is here. The coefficient of kinetic friction between block A and the incline is 0.18, and you can neglect the mass of the cord and the pulleys. What's the speed of block A after it moves 1 meter down the ramp? So I've got speed, I've got distance, and indirectly again, I have forces. These are masses, and I recognize that. But when I solve through the problem, it'll be a force which is associated with weight. And that's what's driving this. Well, so we start out by looking at the absolute motion. So the absolute motion is going to be a function of distances along this orange cord. And so I can write SA, SA, SB. And if I do that, I get twice SA plus SB is equal to length constant. And length constant includes all those extra bits and pieces over here, around the pulley, everywhere that normally I neglect and don't worry too much about. If I look at the displacement, if block B or block A displaces by 1 meter, what that tells me is block B is displacing by 2 meters. And it's also going in the opposite sense of block A. So block B is going to move up 2 meters when block A moves down 1 meter. And I'm going to leave this as an absolute velocity, and if I do that, I can say the absolute velocity of mass B is equal to twice the absolute velocity of block A. In terms of terms I might want to worry about, I might want to worry about this normal force. And I want to get a term or an expression for it. And I can look at this and I can say, well, I have y and x in these directions, and y, there is no motion up or down relative to y. And so sum of forces is equal to 0. So NA minus 4/5, because it's a 3, 4, 5 triangle, 4/5 MAG equals 0. And I get the normal force of 196.2 newtons. If I add all the terms together, and I have both blocks in this system, and this is one of the differences with this problem is that it's a system of particles, and I look at the work-energy equation, I can say, well, work from 1 to 2 plus the kinetic energy at position 1 is equal to the potential energy, or kinetic energy at state 2, position 2. And if I put in all the terms, I have all this here. I have, first of all the terms for kinetic energy, so that's T1. These two terms deal with the work from 1 to 2, and this final term, these two final terms, are associated with the kinetic energy at position 2. I can get rid of VA1, VB1, because both of those terms are 0, because the system starts at rest. I can also get rid of these two terms, the tension, because one, I know that from Newton's third law that internal forces are going to disappear. This is an internal force. But also, if I do the calculation and forget about it, as long as I know what the displacement is, 1 meter positive, negative 2 meters for SB, then these two terms disappear. And so I end up with a simplified equation, not super simple, but one that really depends on components. Now, one thing I would want you to sort of pick out is this term right here and this term right here, which are essentially, if I had solved through for this, I would have had I could use conserved energy, or sorry, potential energy and gravitational potential for those two terms. This term would always stay the same, which is it's opposing motion, and it opposes motion, and so it's work done, and it's a non-conservative force. And then finally I have these two terms here, which are the kinetic energy. I'll get from this that the velocity at position 2, oh, and the other thing I should point out is I said, well, velocity of B2 is twice the velocity of A2. And it's also, I can write it as negative if I'm being very careful, but because it's squared, it doesn't matter. So it ends up VA2 squared plus, and twice VA2 squared squared. And so I end up with VA2, which is equal to 1.69 meters per second. You can see in this, and I hope you do at this point because you've gone through a number of homework problems, the link with conservative forces, and it's gravity in this particular case. So let's do one last question, and one last question is looking at something kind of fun. It's spring, and this is a conservation of energy problem with no work done because I'm going to neglect friction. So I have a 0.25 kilogram pellet that's pushed against the spring and released from rest today. Neglecting friction, determine the smallest deflection of the spring for which the pellet will travel around the loop and remain in contact with the loop at all times. So the loop has a radius of 0.7 meters. The pellet, this thing right here, is 0.25 kilograms, and this shouldn't be capitalized, but it's okay. K equals 500 newtons per meter. And there are 5 positions here. A, the starting position, B, the lowest position on the loop, C, the midpoint, D, the highest position, and E, which is the lowest, or the other side from E. So it's opposed to E, or C. So that's kind of the motion in kind of a gross PowerPoint animation kind of way. And here's sort of where it might end up as if it goes through the whole thing. And of course it stays in contact with the wall over the entire time. So in terms of solution, I have a weight force which is acting downward, starts here and ends up here. So one thing I want to know is what the minimum force is at D. And the minimum force is going to be when the normal force on the block is 0. So that's when weight equals mass times acceleration normal. And so that's going to be weight and G, which is equal to VD squared over R. And if you do that, you get VD equals square root of GR, or 2.62 meters per second. So in terms of potential energy, we can say this is 1, this is 2, and I've taken the high point. I can say, well, velocity or potential energy at 1 is spring potential plus gravitational potential, and that is the unknown compression. Here I've defined my datum, and because this is a particle, that's 0 meters. That's the 0 height. I have T1, which is equal to 0 joules, because it starts from rest. And then I have the spring potential plus the gravitational potential. But now spring potential goes to 0 because the spring is fully extended and it's returned to its uncompressed state. And on the other side, I have the height as it reaches the top of its motion, and that is going to be 1.4 meters. T2, which is equal to 1/2 m velocity at position D squared, and I can set this up. Again, no work done because there are no non-conservative forces here. Everything is conservative. So spring and gravity in this particular problem. And if I substitute in terms, I've got 1/2 kx squared equals 1/2 mvd squared plus mgd. And so put all the terms together, I get x is equal to 13.1 centimeters. So that's the compression I have to bring for the spring in order to have it sort of start properly, or to work properly. Work energy is great. I really like work energy. It's one of my favorite sort of approaches and favorite parts of the course. Conservative forces generally, I mean, typically every time, let's not kid ourselves, are better dealt with using potential energy. And you have the option of solving a problem any way you want to. I just find it's very difficult for me to visualize work for conservative forces as easily as it is for me to visualize potential energy. The important thing that I do want you to pull out of this is this. You need to be able to read a problem, and you'll see a lot of problems in the course where you have force, velocity, and distance and immediately recognize it as a work energy or conserved energy problem. Thank you, and we'll talk again.